In this video, we will be looking at our virtual lab number 2, camping and thermodynamics. Now, the bulk of this lab actually piggybacks off of an idea that we looked at in our first virtual lab. That is the idea of heat transfers. The only difference is that now we're going to get into a heat transfer type known as calorimetry. And so in calorimetry, we are using a calorimeter to measure the heat of a chemical reaction. Now, a calorimeter is an instrument. It can be as simple as just insulated cups, like coffee cups, or as complicated as what's called a bomb calorimeter, where you've got insulated vessel inside of another insulated vessel that is set off in chemical reactions through combustion, usually using electrical charge. They can be, like I said, very simple or very complicated, just depending upon what you're trying to do. Now, in calorimetry, what we are going off of as a concept is that if we are at constant pressure, then the value of delta H, the heat of reaction, or rather the delta H for the process, is equal to the Q at that controlled pressure condition. What calorimetry takes advantage of is we will do a series of reactions in water usually. And what that allows us to do is the reaction occurs in water, and the water increases in temperature or decreases in temperature. And based upon the value of Q in the water, we can get some idea of the value of the pressure control, the QP, the heat transfer for the process of the reaction. But the relationship here is not as simple as it appears. In fact, it's not that they are equal to each other directly, but rather they are equal to each other in opposite. The change that is going on inside of the water is the opposite of the reaction itself. And so if we kind of put all of this together, what this ultimately leads us to is that the heat of a reaction, if measured by calorimeter, is equal to delta H of reaction, and that is equal to the opposite of the heat transfer that is taking place inside of the water. Now, why is this the case? Well, it has to go back to this idea that we've established earlier in this thermochemistry chapter of system versus surroundings. The chemical reaction itself is the system. So when we are putting together an acid and a base and trying to figure out how much heat is generated by that acid and base combining, that is the reaction system that we are looking at. Now, water is not actually part of that reaction system, other than it is a product in the case of the neutralization reactions themselves. The water surrounds the reactants as its solvent, and therefore is part of the surroundings. remember that your law of conservation of matter, or excuse me, your law of conservation of energy says that energy is neither created nor destroyed in a chemical process. So the energy of the reaction must be the opposite of the energy change for the water. And so the energy change of the reaction, which would be the Q of the reaction, is equal to the opposite of the Q of the water. Since Q of reaction is the same as delta H of reaction, if we are at constant pressure, the delta H of reaction, the enthalpy of that reaction, is also equal to the opposite of the heat transfer for the water. And so this concept, this pair of concepts, is at the very heart and key of what this whole everything is about. And so looking at your pre-lab only has the one question. What is the heat of reaction when I combine this substance with this substance? It's going to be following along that same kind of idea. And then your later calculations will get into what is called the molar heat of reaction. And the molar heat of reaction would take this value of energy and divide it by the number of moles of product that are being generated. And so that's where in reactions like this is where we would have to start looking at limiting reactant kinds of ideas. We'd have to start looking at how do the two reactants interplay with each other in terms of how fast does one act up, how much moles, how many particles is it going to create, that kind of thing. Let's go ahead and do a couple of calculation examples just to kind of show what we're going to do. So I'm going to do a reaction very similar to the type that you're going to see in the pre-lab. So I'm pulling this out of your textbook. This is out of chapter 10. And we are going to look at again, a problem very similar to the pre-lab question. All right, so here's an example that I pulled, 10.115. A 100 milliliter sample of 1 molar NaOH is mixed with 50 milliliters of a 1 molar sulfuric acid solution in a large styrofoam coffee cup. Now, the purpose of telling us that particular detail there, the large styrofoam coffee cup here is acting as our calorimeter. All right, temperature of each solution before mixing is 22.3 degrees Celsius. After mixing, their temperature reaches 31.4 degrees Celsius. Assuming that the density of the mixed solutions is 1 gram per milliliter, the specific heat of the mixed solutions is 4.18 joules per gram degree Celsius, and no heat is lost to the surroundings. What is the heat of reaction? Okay, so there's a lot to unpack here. Now, first of all, we've got a little bit of good fortune here in the sense that the temperature of each solution is the same at the start. Why is that important? Because, well, when we're calculating this heat change, if they were at different temperatures at the start, what I would have to do is I'd have to do a heat calculation for each one of the components. So I would have to do a Q is equal to MC delta T for the sodium hydroxide and a Q is equal to MC delta T for the sulfuric acid. And then I would have to add those two together to get ultimately the heat of reaction. Since they're at the same temperature, though, I can combine them together from the start and do just one calculation. So that does save us a little bit of time there. So other pieces of information that are important. We've got 22.3 degrees Celsius. That is our initial temperature. We've got 31.4 degrees Celsius. That is our final temperature. That's going to go toward our delta T. Our C value, we are told that the specific heat of the solution is 4.18 joules per gram degrees Celsius. So that's going to give us our value of C. And the other important piece of information that was given to us is that the density of the solutions we can assume to be 1.00. So if I find out the total volume, which would be 150.0 milliliters, the density would tell us that that is actually 150 grams of solution in total. So from this perspective, we've got all that we need to figure out what the heat of the solution is. So the heat of solution is the mass, 150.0 grams, multiplied by the specific heat, 4.18 joules per gram degree Celsius, multiplied by the change in temperature, 31.4 degrees Celsius minus 22.3 degrees Celsius. And so if I did the calculation for delta T, 31.4 minus 22.3, I would get 9.1 degrees Celsius as my change in temperature. 9.1 times 4.18 times 150 to two significant figures because of this temperature. My Q for the solution would be positive 5,700 joules. Now keep in mind, that is the Q of the solution, but it's not asking us for the heat of solution. It's asking us for the heat of reaction. And remember that the heat of the solution, the heat that the water undergoes, the change that we see in the water is the opposite of what we saw in the reaction. The water got hot because the reaction released heat. So for the heat of the reaction, it would be the exact opposite based on our law of conservation. So negative 5,700 joules would be the appropriate response and since Q of reaction is the same as delta H, we could also say that the delta H of reaction is negative 5,700 joules as well. So that's how to solve, simple problems like this. And the pre-lab question is a problem of this kind and this type, where we're not concerned with the molar heat of anything. We're not concerned with the number of moles. We're just looking simply at how much heat is transferred in the process. But if we did want to take this one step further, we could. So let's say that we've got all of this here. Let's go ahead and wipe it all away, with the exception of the problem itself. So what if we were asked about the molar quantities? What if we wanted to know the molar heat of reaction here and not just the heat of reaction? Well, if we were asked that, then we have to get into some more specifics. And one of the specifics that we have to get into is we have to have a balanced chemical equation, because we need to know the limiting reactant so we can figure out how much product is going to be made in this process. So for that, we need to look at our balanced chemical equation. Sodium hydroxide reacts with sulfuric acid to make sodium sulfate and water. And if I balance out that equation, wouldn't you know, it's not 1-to-1, it's actually 2-to-1. So the real question in front of us is, now that we have this information, what's the molar heat? So how many moles of sodium sulfate were made in the process? Now, to answer this question, we're going to have to go through a solution stoichiometry to find the limiting reactant, to find this information out. Luckily for us, we can use a little bit of a trick to get us to that spot, as opposed to going through kind of the traditional solution stoichiometry limiting reactant kind of problem. The trick here is something called the millimole method. In the millimole method, we will find the number of moles by multiplying the molarity of the solution by the number, by the volume in milliliters. And the reason we do this is, with solutions in particular, we tend to run with small numbers. Millimole method helps us to get large numbers that are easier to compare. So if I take 100 milliliters multiplied by 1 molar solution, I have 100.0 millimoles of sodium hydroxide. If I have 50 millimoles times 1 molar sulfuric acid, I have 50.0 millimoles of sodium, or excuse me, of sulfuric acid. I can convert both of these into moles simply by applying the mole ratios. So one mole of sodium sulfate for every 2 moles of sodium hydroxide. That would give me, for the sodium hydroxide, 50 millimoles of sodium sulfate from the base. And if I applied the same kind of logic up here, 1 mole of sodium sulfate for every 1 mole of sulfuric acid, it's a 1-to-1 ratio. I would get 50.0 millimoles of sodium sulfate this way. So all that conclusion just gets us to the point that we have equal molar amounts in terms of reaction. We have equal molar amounts. So as a result, we have a stoichiometric amount here. Neither of these are limiting reactants. If there was a limiting reactant, we would need to choose the smaller amount of millimoles. But what we can do now is, now that we know that we're going to create 50 millimoles of sodium hydroxide, we can convert that into moles. To find the molar heat of reaction. I would take that negative 5,700 joules that I calculated before, divide it by the 0.0500 moles of product. And that would give me negative 110,000 joules, or negative 110 kilojoules. Again, this is joules per mole and kilojoules per mole. So now we're dealing with much more serious numbers, numbers that kind of make sense given the quantity and the amount of heat that's generated by these neutralization reactions. So you'll see this kind of problem in the data and calculations, the results section of the experiment, but I wanted to kind of give you a heads up on it now so that when you get to that point, you don't necessarily get stuck on that point. So if you were asked the molar heat of reaction, that's all you have to do. Draw up the balanced chemical equation, figure out the limiting reactant, figure out which one gives you the least amount of product, and go off of that. Now, a question that some of you might ask is, well, why didn't we convert this to water? Well, if you can see there, the coefficient for water is 2. And so we would end up getting a heat of reaction that was not to 1 mole, but rather to 2 moles of water. So whenever you can, if you have a product that has a stoichiometric coefficient of 1, use that one. If you don't, just keep in mind that you're going to have to multiply whatever number that is that you get by the coefficient to get the correct value for the molar heat, because the molar heat is always going to be per mole of product, not per 2 moles of product, not per 4 moles of product, but per mole of product. And so if you have a product that already has a coefficient of 1, that's the easiest way to go. If you don't, then you'll have to do a little bit of manipulation. That's all for this particular pre-lab video. Thank you for your attention, and I will see you next time in lab. Have a good day.